moving on to what our second derivative tells us about a function. So similar to the first derivative, knowing if our second derivative is positive or negative tells us about our function, but not its increasing or decreasing, but about its concavity. So if f double prime is greater than 0, that means if my slopes, if f prime is increasing, f double prime is greater than 0, my slopes keep getting more and more positive. My function is concave up. If f double prime is less than 0, if f double prime is negative, which also means if f prime is decreasing, if my slopes maybe start off positive and just get more and more negative, then f is concave down. And finally, if f double prime equals 0, then f has a possible inflection point. It's not necessarily an inflection point. You still have to check and make sure concavity changes. We have a possible inflection point, which we like to call pips. So to find concave up or down intervals, it's very similar to finding increasing and decreasing intervals. First, we find where f double prime equals 0 or is undefined. We find those possible inflection points. Then we draw an f double prime sign line. And remember that inflection points are when f double prime changes sign. We can look at whether our f double prime sign line shows us positive or negative intervals for concave up or concave down. So let's do an example. We're going to find where this function, x to the 4th over 12 plus 1 over x, is concave up or concave down. Let's start by finding our first derivative. I'm going to work over to the side because there's a lot to do on this one. Please, please, please do not do quotient rule on x to the 4th over 12. Remember, this is really just 1/12 times x to the 4th. So we can just do regular power rule on this. Bring the 4 down, and we get 1/3 x to the 3rd. The derivative of 1 over x, again, I wouldn't use quotient rule. Hopefully you have it memorized. That's negative 1 over x squared. Or you can do power rule by making that x a negative exponent. That's our first derivative. We don't need to set it equal to 0 because we already, because we don't want to know increasing and decreasing. We want to know concave up or concave down. So we're going to go ahead and take our second derivative. Again, just more power rule. Bring the 3 down, we get x squared. And then the derivative of negative 1 over x squared, we can think of that as negative x to the negative 2. Bring down the 2, and we get positive 2 times x to the negative 3rd. Positive 2 over x cubed. Now we want to figure out where this is equal to 0 or undefined. We do actually have a point where it's undefined. If you look at that x in our denominator, we know x equals 0 is a critical point because it makes our second derivative undefined. We can also solve this equation for x to figure out our other, oh sorry, that is not a critical point, possible inflection point. We can also finish solving this equation to find where our second derivative equals 0. To do that, I am going to move the 2 over x cubed to the other side. Then I'm going to multiply both sides by x cubed, get x to the 5th equals negative 2. And to get x by itself, we can take the 5th root of negative 2. Remember, you can take odd roots of negative numbers. So x equals the 5th root of negative 2. Our possible inflection points are 0 and the 5th root of negative 2. Not very pretty, but it's where our second derivative is undefined or equal to 0. let's put those possible inflection points, I hope that's what I've been calling them. Let's put those possible inflection points, remember they're not critical points, on an f double prime sine line. We're going to put the fifth root of -2 first because it's negative, and then we'll put 0. And we'll test those intervals in our derivative function. The fifth root of -2. I don't really know what that is, but I know that it's smaller than -10. So I'm going to try -10 as the number that I plug in. If I do -10 squared, I get positive 100 plus 2 over -1,000. So 100 plus -2 over 1,000, I know that that's going to be positive. I also know that the fifth root of -2, it's got to be bigger than -1. So I can plug -1 in. And if I do, I get 1 plus 2 over -1, or 1 minus 2, and I get a negative value there. And then if I plug in 10, positive 10, I get 100 plus 2 over 1,000, which is positive. And so I can say that my function f is concave up from -infinity to the fifth root of -2, union 0 to infinity. And f is concave down from the fifth root of -2 to 0. There's an example of how to find concave up and concave down intervals. Also note we do have inflection points at the fifth root of -2 and 0 because f double prime changes sign.